So then we need some good approximation methods, and we will look at two of these. One is the nearest neighbor algorithm. So these are the steps that we're going to use to find the optimal solution. We'll model the problem with a complete graph, identify the vertex that serves as a starting point. Right? For these problems, it will tell you where to start for the nearest neighbor. From the starting point, choose an edge with the smallest weight that's connected to your starting vertex. Hit that vertex. Choose the edge with the next smallest weight from that vertex that does not go to a vertex already listed. And you don't want to close the circuit too early. So we will continue doing this until all vertices are hit. Just make sure, again, you don't close the circuit too early. Again, our last edge we will return to the starting point since we are doing a circuit. So we will do at least one example of these. A sales director who lives in city A is required to fly to regional offices in cities B, C, D, and E. The weighted graph gives the one-way airfares. Use the nearest neighbor method to find the approximate solution. And what is the total cost? So again, we are starting at A. We are not using brute force. We're using nearest neighbor, which is a lot less time consuming. So from city A, we go to the least cost city. So if from A we could go to E, which is 128. Right, if we went along this route, that's 128. If we went to D, that's going to cost 147. Again, that's just listed from A to D. From A to C is 114. And if we go to vertex B, that's 180. So the nearest neighbor means we start at vertex A and we go to the cheapest place. Okay, so we want to find the cheapest one of these. So it looks like C costs the least to go to C. So from A, use your highlighter in your notes. Oops, you don't need it to be that thick. I just went off course there. From A, we will go to C. All right, which costed $114. We might as well add them up because it tells us to find the total cost. Now we're at vertex C, and we are not going to go back to A, obviously. We've already been there. So from C, if we go to B, it's 116. Right, from C to B, it's 116. Or we can go to E, which is 115, or you can go to D, which is 169. Right? You cannot go back to A, so you only have 3 choices, and we choose the cheapest, which is we will then go to E. At 115. Might as well find the total cost as we're going. And then in step 3, we're at E, and we're not going to go back to A yet. We're going to hit A last, so we still haven't visited B and D. So we could go to B for 195, or we could go to C for D for 194. All right, we've already been to B, C, and E, so we can go to B or D, and we will go to the cheapest, which again is this one. So we will hit D next at 194, and then we have to hit B, right? So we go to D, and then we have to hit B. If we go from D to B, that's 145, the only one that hasn't been hit, and then we have to go back to A. Right, so we go from A, C, E, D, B, A, and then you want to make sure all the vertices are listed there, and obviously the only one that would repeat is the starting and ending vertex. which is A. So then you want to add those up. 114 plus 115 plus 194 plus 145 plus 180. Didn't seem right. 114 plus 115 plus 194 plus 145 plus 180 is $748. So we can't say, we can't be 100% sure that this is the optimal solution, right? But it is an approximate optimal solution, right? The nearest neighbor does not get necessarily, it could, but it may not necessarily give the optimal solution, but it does a good job. I guess we will do one more of these nearest neighbor. Use the nearest neighbor algorithm to find the city that would be visited third, assuming the salesperson starts at city C. So we're starting at city C. So you don't have to write out the steps. You can just kind of look at it if you want. From city C, you can go to A for 124. You can go to B. Again, we're starting here. You can go to B for 126, or you could go to D for 179. All right, and we choose the least cost, and that would be A. So we're going to go to A next. So then with step 2, we visited A, so now we can either go to B or D. From A to B is 190. From A to D is 157. So we're heading to D next. And then you have to visit B. All right, and then you would go back to C. And the question said, use the nearest neighbor algorithm to find the city that would be visited third. All right, so we're starting at C. So A is visited first, D is second, and B would be visited third. All right, we're starting here. So we go 1, 2, 3. B. So that is nearest neighbor. It will give you a starting vertex, and you stay kind of connected the whole time as you're doing it. The next algorithm is called, and the last algorithm is called the best edge algorithm, or sorted edges or cheapest link. It actually has several different names. And again, it is approximate method. The brute force is the only one that guarantees the optimal solution. This one, you're not going to be originally given a starting vertex, although it might tell you to write your answer starting with vertex B. But this one, and you don't kind of stay connected like you do with the nearest neighbor. You list all the edges weights from smallest to largest. I kind of only do that if it's a large graph. You know, if it's small enough and you can kind of eye it up to see which one's the next smallest, you can just do that. And you pick the cheapest link, i.e. the edge with the smallest weight. In the case of a tie, pick either one and highlight it. And this is when it's nice to use a highlighter. Pick the next cheapest link available and highlight it. And keep going, but remember, don't close the circuit too soon, right? You have to have visit each vertex, and each time you're going to go into a vertex and back out of the vertex, so you will not ever create 3 edges coming out of a single vertex. There should only be 2. And then lastly, once you get done, you'll connect the last 2 vertices and to close the circuit. So let's see how this works, this best edge example. So again, we are not going to, we don't actually even have a starting point. It doesn't even tell us to. I mean, down here at the bottom, it says the cheapest link doesn't have start at a particular vertex. Instead, write the solution starting with the indicated city, vertex or city. And this one doesn't even give us a starting one. Okay, so if you're one that you can just look at all the weights and highlight the cheapest one and just, okay, I'm going to eye them all up and I can see that this is the cheapest one. This is, here is step one is this one. But if you want to, you can put them in order, 30, 39, and make sure you have them all. The next cheapest is 41 and 45, 62 and 77. Put them in order and then just count again, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and make sure that you have the same number. All right, that's also a good approach. Okay, so we're going to highlight the 30. So this one's going to be, and the advantage to writing them out is then you can circle the ones that you're going to use and then you can add them up at the end. So next is 39. It doesn't even have to be connected. I'm not going now from D anywhere. You're not starting anywhere. You're just picking the cheapest link. So 39, that's fine. So I'm going to circle it because I'm going to include it. Now the next one's 41, but I don't want to use 41 because that will close my circuit too early, right? I'll have exactly this circuit right here, and I can't close the circuit too early, so no on that one. 45, again, if you don't want 45 because that would be 3 edges. And you can only have 2, right? Because with the circuit, you're going to have it going into C and back out of C. So you can't, and that was on the last slide, that you can only have 2 edges coming out of each vertex. So then the 62 is the next, and that's good. We'll circle it. And then, of course, we close it and go back. And so we will take that one. So that is our least cost circuit using the best edge, which is also called the cheapest link. And so we can, and you can start it. It didn't even tell us what vertex to start with, so we can start with wherever we want. A, C, D, B, A is how we would write that. A, C, D, B, A, or you could write it backwards, A, B, D, C, A. It doesn't matter. It also says if the weights are distances in miles and the gas is approximately 25 cents a mile, what is the approximate cost of the cheapest trip? So we're going to have to add up the total number of miles for our trip up here, the ones I have circled. 30 plus 39 plus 62 plus 77. So I get 208. So it's 208 miles, this trip. And it says if gas is approximately 25 cents a mile, what is the cost of the cheapest trip? So we've gone 208 miles and it's 25 cents a mile. So we would get $52, right? A quarter of that is $52 for that trip. So we will have one more example of this. And that will be the end of this section. Find the approximate minimal cost circuit if the salesperson starts at Saginaw. Again, this is the best edge example. We don't start at Saginaw and use the nearest neighbor. We're using best edge, which best edge is you don't start at a particular vertex. So let's just remind ourselves we don't start at particular vertex. We might write our answer, our final answer, starting at Saginaw. Particular vertex. So don't start at particular vertex. Remember, no 3 edges coming out. and no circuit too early. That's the thing that you have to watch out for. So again, if you want to write the edges out in increasing order, because then you can rearrange them if you've messed up, I'm just going to kind of eye it up and see if I need to make any adjustments. 56, and then somehow mark it when you write one down so you know you have them all. It looks like 98 might be next. 113. We have 133, 135, 137, 142, 147, and 167. All right, and again, count them all, make sure that you have them all listed. And again, you don't have to write them all out if you're pretty good at eyeing it up. But if you do write them out like this, you'll realize if you have a smaller one listed after a larger one, etc. So let's go ahead and start. Again, we do not start at a particular vertex. We just do the cheapest link and circle it. The next cheapest link is 58. Again, it doesn't even have to be connected to the other one. Then we have 98, which is here. The only thing we have to watch for is that we don't make a circuit too early. Like I would not want to go to close or put a line between Saginaw and Toledo, because that would close the circuit too early. And I don't want 3 edges out of a vertex. So Detroit I know is done because it has 2 edges coming out. 113 is next. And that's fine because that's still 2 edges out of here, 2 edges out of here, and I haven't closed a circuit. Oh, this one ended up turning out to be pretty easy because 133 is next, and that's actually closed my circuit. And so I'm good with that answer. Find the approximate minimal cost circuit. So now I just add them up. $133. So I get, when I add those up, $458. Let me check one more time. Yep, 458. And that could be miles or cost. Find the minimal cost circuit. So it could be written like that was the total cost. It actually said find the approximate minimal cost circuit starting at Saginaw, so I actually didn't need to find the total cost, although I did. But Saginaw, so you can go around this way or the opposite way. It doesn't matter. Saginaw, Detroit, Toledo, Kalamazoo. I'm assuming that's supposed to be Grand Rapids, and back to Saginaw. Okay, or the other direction. It doesn't matter. So that is the end of section 14.3.